Hi everyone, I'm Steve Ahlswede, and I'll be presenting one of our recent works, Weakly Supervised Semantic Segmentation of Remote Sensing Images for Tree Species Classification based on explanation methods. This work was a joint collaboration between the Remote Sensing Image Analysis Group and the Geoinformation in Environmental Planning Group from the TU Berlin, and the project was funded by TreeSat AI under BMBF. So, accurate identification of tree species by the analysis of remote sensing images is important for various forestry applications. Tree species mapping can be achieved via semantic segmentation, which refers to the task of classifying individual pixels within an image. One of the main bottlenecks for deep learning models is the large amount of labeled samples required during the training phase, which are not often available for tree species and can be expensive to obtain manually. One solution to this problem could be to generate labels at the image level rather than the pixel, as this will greatly reduce the amount of effort required for image labeling. However, semantic segmentation models cannot be made operational using image level labels, as they provide no specific information of the present classes, and thus the model only learns how to make predictions at the image level. Thus, we investigate the effectiveness of explainable neural network approaches in the context of weakly supervised semantic segmentation. As such, we can obtain pixel-level predictions using only image-level labels as our training signal. Explanation methods provide information on which pixels contributed most strongly to the given image-level prediction in the form of heat maps. And such heat maps provide higher confidence scores for locations related to the class prediction, and thus can provide relevant information regarding the location of image-level predictions from the model. So the aim of this work was to obtain accurate pixel-level classifications of tree species using only image-level labels during training, and to investigate the applicability of explanation maps within the framework of weakly supervised semantic segmentation. In particular, we investigated 4 methods: CAM, GradCam, PCM, and SEM, and I will now explain each in a bit more detail. So we're going to start with CAM, and so the goal of CAM is to exploit the learned feature maps from a CNN in order to obtain a set of class-specific activation maps. And so this is achieved by inserting a 1x1 convolution layer after the final features of the CNN, which then outputs a CAM for each class. The 1x1 convolution layer learns a set of weights, which give the importance of each of the feature maps with respect to a target class. So here we have 512 weights for class 1, and the same for class 5. And the key thing to note here is that after the 1x1 convolution, each of these maps is globally averaged into a single value, which is then used directly as the logit score for that class, and this ensures that each map we learn is truly class-specific. So for a CAM of a single class, we use this formula here, and so on the left we can see a graphical representation. So for a CAM, we perform a weighted sum of the feature maps from the CNN denoted as F. So for class 1, we would take the class-specific weights and use them to reweigh each of the previous features, and after this reweighting, we then sum them together to obtain a CAM, which can then be used later for semantic segmentation. So now moving on to GradCam. Here the intuition is the same, as we use the same general formula of reweighting the feature maps. However, the formula for obtaining the weight term is different in this case. So now instead of learning the weights via the 1x1 convolution, the weight value is calculated as the mean gradient value of the feature map with respect to a given class prediction, which is this entire formula here. And so we need to perform a backpropagation step for each of the classes that we want a CAM for, such that we can get the gradient with respect to that specific class. Moving on to PCM, this method builds upon the original CAM, so we still calculate the CAM as described earlier with the 1x1 convolution layer, but now we aim to further improve the CAM by exploiting correlation information within these features of the model. And so here's a diagram showing the self-attention technique used within the PCM module. Features within the CNN are passed through 2 separate 1x1 convolution layers. These are then reshaped and are multiplied together so that we can get a similarity matrix here. The similarity matrix is then used to calculate a weighted sum of the CAM, which gives us the final output of PCM. So the final method that we applied was self-enhancement maps, and just like with PCM, SEM calculates the CAM using a 1x1 convolution layer and then exploits correlation information from the final feature maps in order to improve the CAM. However, SEM calculates the similarity only for a small subset of the possible pixels, whereas PCM calculates it across all pixel pairs. So here in SEM, we choose the K top pixels, which are the pixels with the highest values within the class CAM. And so if we were to set K to 1, then in this example we would only take the similarity between this pixel location in red here, as it has the highest score within this CAM. And so we would then calculate the similarity between this pixel and all other possible pixel locations. And since the CAM and the CNN features are of the same spatial dimension, we can map a feature vector of the CNN features to the location of the kth pixel within the CAM. And this allows us to then calculate the cosine similarity between these feature vectors, which then make up the values within our kth similarity map. So in practice, we would set K to a value higher than 1, ending up with K similarity maps for a single class. And we would then want to aggregate them into one final output for that class, which we would then use the maximum function across the channel dimension. So now to describe the data set, we had a set of 20,000 images taken across the region of Lower Saxony, Germany. Images contain 4 bands with a spatial resolution of 0.2 meters. Image level labels were obtained by assigning the dominant species within our set of polygons, which overlapped with the images. And in order to test the final segmentation maps, we rasterized these polygons. And here we had 5 classes: pine, spruce, beech, oak, and cleared. For our experiments, we used 3 metrics in order to compare the 4 methods. The first was the ability to perform accurate tree species mapping. The second was model complexity in terms of the number of model parameters required for each approach. And the final was segmentation time in terms of milliseconds per segmentation map on a single image. And all models used a DeepLab v3 architecture. So in this table, we can see that SEM had the best performance in terms of F1 score, with CAM obtaining the lowest. In terms of model complexity, PCM was the only one that required extra parameters due to the PCM module having the 2 additional convolution layers during the embedding of the CNN features. And finally, the segmentation time was the fastest using CAM, and it was followed rather closely by PCM and SEM. And grad CAM was significantly slower due to the need for additional backpropagation step at each individual class. And here we can also see some qualitative results from the 4 methods. As we can see, SEM achieves very good segmentation, sometimes even being better than the reference map. And one area where all 3 methods struggled was when separating very similar species, seen down here. So this is oak and beech, which are both deciduous trees. And since we only had 4 bands available, separation within the feature space between classes with similar visual features, such as broadleaf, was difficult and led to confusion. So in conclusion, we examined 4 explanation methods within the framework of weakly supervised semantic segmentation to obtain tree species maps using image level labels. Our results showed that all explanation methods can be viable for weakly supervised semantic segmentation. However, the results showed that SEM to be the most promising of the 4, as it yielded the highest segmentation scores, had a low model complexity, and achieved a fast segmentation time. Here we analyzed weakly supervised semantic segmentation for trees. However, such an approach can be relevant for other semantic segmentation problems in remote sensing, and we are planning to examine this as a future work. As an additional future work, we also plan to further assess explanation methods for providing pixel-level pseudo-labels for training a semantic segmentation model. Thanks for your attention.